Okay, and welcome to chapter 3. So this is all about continuous random variables. So we're going to take the stuff we learned in chapter 2 about discrete random variables and see how we do it with things now that we're going to call continuous random variables. So this is lecture 13. Here's the motivational example for you to have a try in your own time. At the end of this chapter, I will obviously, as well as doing a case study, we will come back and have a look at this. So often we're not counting stuff, we're measuring stuff. If you think about things like time, height, weight, these are things that can take any possible value in a range. And you don't have a countable set at this point. You have one we'll call uncountable. That is, if you look at weight, it can have any value in a range. You can't just have a discrete set of values, and we need to be able to deal with that. So the first thing we're going to introduce, we'll sort of briefly introduce this, then we'll go away to CDFs and we'll come back to PDFs. We're going to have a new thing. We don't have a probability mass function anymore. We have what we call a probability density function. And this is going to be a function that takes the sample space and basically maps it to the non-negative real number line. So basically from 0 to infinity. And the whole idea, and I'll come back to this in a second, is you don't use the probability density function to get probabilities directly. That is, you don't substitute in a value like we did before. What you do is you integrate the probability density function to get probabilities. But before that, let's sort of say, why is this called continuous random variables? So let's recap the cumulative distribution function. So remember that we're going to define it as, and it's the same for both discrete and continuous, the capital F of y, the cumulative distribution function, is the probability that y is less than or equal to y. And now y will lie all the way between minus infinity to infinity. So this gives us a very simple way. Now when we want to work out a range of stuff, well, that's fine. We can do less than or equal. We can get a way of dealing with this now uncountably infinite thing. So what are the properties of this? Well, we're going to have these following properties. First of all, as we go towards minus infinity, f of y goes to 0. As we go to infinity, it goes to 1, and it's a non-decreasing function. So let's draw a picture of what we mean by this. So if we've got our y here, and we've got our f of y, what we mean at this point is basically our distribution, when we go towards minus infinity, is going to be 0. Then it's going to go up. It can go straight and up, but it's always going either straight or up, and eventually it will get to 1 as we get larger and larger as we go towards infinity. So the main thing is, at no point when I'm drawing this function does it go down. It can stay the same or it can go up, but it doesn't go down. And we're going to define that if, when you look at this function, it is continuous, there's no jumps in it, we will say that the random variable that corresponds to is a continuous random variable. Now there's actually extra constraints. If you go and look at the notes, you'll see the extra constraints there. But generally in this course, if I give you a CDF and it's continuous, then that is from a random variable that is defined to be continuous. As I said, go and have a look at the notes if you want to know the full definition. So how do we exchange between these two things? Well, the nice thing is, if I have the CDF and I want the PDF, then all we have to do is differentiate. So basically the PDF is the first differential of the CDF with respect to y. Okay? This will come really useful. Later on we'll look at how we get the distribution of a new random variable from an old one. And there is a method called the CDF method, and once you've got the CDF, you can get the PDF by differentiating. So we can now write again that our f of y can be, now I want you to notice something subtle here. Here's my CDF, and I get it by integrating from minus infinity my function. But notice how in my function it's no longer y, because I actually want to differentiate up to y. And so I've just put a dummy variable in there. I've replaced all the y's with t, so I know that the y in the input and the y in the function are separate. And that's a technicality that you really need to be careful of. So given that, how do we now know? So we had our rules. Remember when we had the probability mass function, you could say, well, is it a valid probability mass function? And we had to find that all the values lay between 0 and 1. And when you add them all up together, you got 1. Well, now the equivalent of PDF is, first of all, our PDF must be always greater than or equal to 0. And the other thing is that if we integrate from minus infinity to infinity our PDF, we should get 1. So here's an example. We've got this PDF that I've given you. It's called 3y squared for the values between 0 and 1. Everywhere else is 0. And the question is this a valid PDF? Well, let's think about it. The first thing I'm going to do is we're going to draw it. So here is my y. Here is my f of y. And the first thing is from 0 less, in fact, let's put this in green. The function is 0 for all this area. And in fact, if we get to 1, it's 0 there. Well, what does it look between 0 and 1? It's going to look something like that. Bit of a parabola, it's curved. This point here is going to be at 3, because y is one of that point, so that's 3y squared. Now, that looks like it's always basically 0 or greater, but we could check. First of all, we know that from out less than 0 and greater than 1, it's 0. That's by definition, we don't really need to check that. But what about the area in between? What about for y less than or equal to 1, less than or equal to 0? Well, first of all, I can square by all sides. So I can basically get that this is the same as 0y squared is less than 1. Because if y lies between 0 and 1, y squared lies between 0 and 1. And also that also means that 3y squared must lie between 0 and 3. So always greater than or equal to 0. So the thing we need to do is we need to check that if we integrate from minus infinity to infinity f of y dy, that should be equal to 1. Well, because this PDF is defined over 3 regions, we should split it into 3 regions. So the first region is from minus infinity to 0, and f of y at that point is 0 dy, plus the next region is from 0 to 1. In this case, it's 3y squared dy, and then the final bit is from 1 to infinity, 0 dy. Well, that is 0, and that is 0. So we just have to check the middle bit. So we've got 3y cubed over 3. Why do we get that? Because we know that if we integrate x to the n, that is equal to the x to the n plus 1 over n plus 1 plus c. So I've just used that. And we are going to do that from the value of 0 to 1, which is 1 minus 0, which is 1. Good. That all seems to work fine. So how do we get these probabilities? Well, basically all you have to do is integrate under the PDF. That's how we get probabilities. Rather than substituting in a value, we're going to integrate. So here's my picture. So I've got my function. This is my function f of y. It's my PDF. And if I want to get the probability that y lies between a and b, I just calculate this area here. So we do integration a lot. Before we do that, let's have a think about, well, a simple problem. What's the probability that y equals some pre-specified value, say y0? Well, you'd integrate from y0 to y0 f of y dy. So that would be whatever your integral is, let's call it f of y, and we will go from the value y0 to y0, so that's going to be f of y0 minus f of y0, which equals 0. Which sort of makes sense, because what would you actually be doing if this is, y0 here? We want to know what the area of that line is. And in maths, we consider that lines have no area. So we no longer have the equivalent of a probability mass function. We no longer have a way of saying, what's the probability that y equals y0? In fact, that's a key idea of continuous random variables. I can ask you the probability between two values, but I can't get the probability is equal to a value. Now, we've got a random variable, the same one before. We know it's valid, and now I want to calculate the probability that y lies between a quarter and a half. So let's do that. So let's clean up. Let's draw my diagram from before. So we had our function was 0, then it goes up to 3, 1, and then it's 0. And what do I want? I want to get the area between a quarter and a half. So that's a quarter. So I want to calculate that area. So the probability that y lies between a quarter and a half, we're going to integrate from a quarter to a half, when we know that in this, as we know, in this region here, this function is 3y squared. So this is going to be 3y squared dy. So it's going to be 3y cubed over 3 from a quarter to a half, which is going to be a half cubed minus a quarter cubed, which is 1 over 8 minus 1 over 64, which is 0.1094. Remember, we're still doing probabilities. If you do that integration and you get something that's either negative or greater than 1, you've made a mistake with integration, go back, redo it. So we'll stop there. Next time we will come back and we will look at the expected value of a continuous random variable. Okay, see you next time.